Hi there. Today I'm going to talk about what we are talking about in calculus. Um, Calculus is one of my favorite parts of math, so I think it's very interesting how it works. And I know that a lot of people just memorize formulas and don't entirely understand what we're talking about here, so I'd like to take a minute and try to explain it in a way that will make sense. So this is the graph of y equals, or f of x equals, if you prefer, x squared. Okay, that's what we have right here. There are two parts to calculus. One of them is derivatives, the other one is integrals, and this is very basic. I know that it's a lot more complex than this when you really get into it, but again, this is going to be a short video, so I would like to keep things to the simplest they can be. When we have a function or a curve, if we take the derivative of that at a specific point, say this one right here, if we take the derivative and plug in that point's x value, it is going to give us the slope at that one singular point. If we were to take an integral or an antiderivative, we would have to plug in 2 points. And I'll call this x plus h, just, arbitrary distance away from x. What a definite integral gives us is the area underneath the curve formed by the x-axis, the curve itself, and the vertical lines formed by going straight down from those 2 points to the x-axis. We get that 2D shape that has this curvy top right here. So that is what integrals will give us when we plug those in. And derivatives, the main point of those is to get the instantaneous slope, as I said. So I'm drawing this line, so we would get this line's slope. It touches that at one point and nowhere else. So in order to do this, it uses some basic algebra thoughts, at least. And how we actually come up with derivatives is one of my favorite little proofs to go through. So it is 2 in the morning, as you can see down there, so hopefully I'm not too tired to do this. So let's talk a little bit about about this. I'm going to keep the points x and x plus h up there. I like those 2 points. We're going to need those, okay? So if we labeled these points as x1, y1, and x2, y2, then we would be able to take the slope between them, right? It would be like that. We could find the slope of a line that goes between them using our old algebra techniques of the change in y over the change in x. That's how we learned to find slope in Algebra 1, or maybe pre-algebra. But someone said, well, that's 2 points, right? Like, look, there's all of this space in here and stuff. I just want the slope at this point right here, that one right there. So how can we do better? And I said, okay, well, let's just think about this a little differently. I'm going to call, like I said, I'm going to use these names down here. So instead of x1 and x2, it'll be x and x plus h. Okay? That way we only have to deal with one x value. Then we just have some arbitrary distance away from x, right? Okay, so now I'm going to talk about it in terms of f of x. Well, we would have x and f of x, because y is equal to f of x. The second point would be x and f of x plus h, or that distance in addition to x. So now, using these 2 points, which are the same as these 2 points, just written differently, which are the same as these 2 points, just written differently, let's plug them back into our formula and see what happens. Well, on the top, this was the second point, so I'm going to start with those. We're going to have f of x plus h minus f of x. Okay? On the bottom, we're going to have x plus h minus x. But look what happens. We have an x and a minus x, so those can cancel out. What that leaves us with is f of x plus h minus f of x over h. So what we want, looking back at our graph, is for these 2 points to be the same point, right? We want to only be able to use one point. For those to be the same point, h would have to be 0. Because if we add 0 to things, then, it doesn't change. So we looked back at this formula down here, and we said, what if we just pretend that it's going to be 0? Now we can't plug 0 in, but we can pretend, right? And we're going to do what's called taking a limit. Whoops, I wrote x, as h approaches 0. And this is one of, I think this is like the alternate second fundamental theorem of calculus or something, but this is my favorite one, because of how much sense it makes when you derive it through that basic slope formula. At this point, what we can do is actually plug in some stuff. So we're going to use our formula of f of x is equal to x squared. So let's plug that in. We're going to take the limit as h approaches 0. Instead of f of x, it's going to be x plus h squared. Because whatever we plug in there, we're going to square. Minus x squared. Still just over h, though. Let's keep going. The limit as h approaches 0. We can use our FOIL method, or if you know how to do this, you square the first one, square the last one, and double the product of the two. So 2xh plus h squared minus x squared over h. Notice we have a x squared and a minus x squared. Those will go away. Now we're left with the limit as h approaches 0 of 2xh plus h squared over h. Now, everything in this has an h, which means we can divide it out. We cancel out that h with that, and get rid of one of the h's from the squared. What we're left with is the limit as h approaches 0 of 2x plus h. And we said, well, now h is allowed to be 0 because we're not dividing by it anymore. So the derivative, or f prime of x, is going to be equal to 2x. You're thinking, what does that possibly mean? But remember, we had an x value up here. Let's say that that x value was 2, and I want to know the instantaneous slope at the x value of 2 of the function f of x squared. All that I have to do is take that x value and plug it in here to this new function that we found. F prime of 2 is going to be equal to 2 times 2, which is going to be equal to 4. So, in our graph of y equals x squared, or f of x equals x squared, the instantaneous slope at the point x equals 2 is 4. That's all that derivatives are talking about. Now there are some practical applications in the real world for stuff like that, but as far as what a derivative is, that's all that it is. Now what is very fancy is in math we always have inverses, right? We have plus and we have minus. We have times and we have divide. It's the same for this. The inverse of a derivative is the integral, and it just so happens that if you do an integral, it gives you the area under the curve, and that's going backwards. But this video is getting a little bit long for what I like to upload, so hopefully this helped you understand at least the basics of what a derivative is talking about, which is that instantaneous slope at a single point rather than having to use 2 points like we used to in algebra, as well as what an integral is talking about, which is that area underneath the curve between 2 points for the nice three nice perpendicular sides, and then one curvy side that would normally make things very difficult for us. Instead, it lets us take a very nice area of that. And then it had, like I said, it has applications in physics and all sorts of different things, and it gets much more complex as you put in the z, and you start taking in 3D shapes and all crazy stuff like that. But as far as basics go, that is about it. Hopefully this helped you understand that. Again, I'm very sorry for rambling, but I will once again point out 2 in the morning, and I'm just making these videos, having some fun. So yeah, good night.